Good morning. Today we're going to talk about Sirius, a flat data center with nanosecond optical switching. Today we are in the world of fast computing and communication. Cloud systems have made the work even faster. The expectation of computer engineers are growing so fast in the lieu of cloud systems that the owners of cloud computing systems have taken a giant leap in designing and developing their network and computer infrastructure. Today we're going to talk about one such system. Before going into the details of the system, let us define the current cloud computing and switching system and how the data is handled, routed, and finally delivered to the end system. Switching is the process of using same network lines capable of connecting multiple endpoints based on MAC addresses. It's implemented traditionally using transistors, mostly CMOS. Based on MAC addresses, data is routed appropriately. This is the core of switching. Reconfiguration of switches. In order to make switching possible, we need to reconfigure the switches so that the task of multiplexing can be achieved. We need switching to be very fast so that the user thinks that he completely owns a dedicated line, not a shared one. Hence, the reconfiguration needs to be fast and automatic, and no human intervention is the ideal way to go. Queuing. Traditionally, the core network infrastructure between which causes heavy loads to be mitigated is the queues. These queues are used to buffer up the data when the lines are busy. It has been the most prominent data loss prevention mechanism for many days, for many years. On-demand scheduling. On-demand scheduling is the next step after queuing, where multiple nodes are interconnected in order to prevent excess load on one single line. This on-demand scheduling tries to allow data on several different lines by computing on the fly the demands of the user and hence having a demand scheduler to decide which route to choose, thereby aiming to prevent congestion for customers. In all of this, where does Moore's law comes? Moore's law states that the bandwidth doubles every 2 years at same power and cost. However, doubling the scale of electrical switches that necessarily resulted in doubling of cloud traffic. Cloud traffic seems to be increasing so rapidly. This requires enormous scaling of current system to meet such a demand. Scaling generally means adding more components, and more components adds more cost and more power. This in turn requires a lot of maintenance, which leads to poor flexibility in future workloads. Current switches do not meet these requirements. Why are these factors important? Moore's law imposes a limit on free scaling and tells us that normal free scaling cannot achieve demands. Reconfiguration needs to be very rapid, and the current switches tend to have enormous delays associated with them due to their way of operation. Queuing adds a significant burden to the network, which at scale is huge, and maintaining queues can be overwhelming. Also, scheduled computations on the fly can be very costly and time consuming, especially when the loads are time critical. And this on-demand scheduling requires special circuitry and mechanisms which have to be maintained and installed, which are again prone to failures. So switches restricted us from scaling. Can we think of an alternative to electric switches? Switches is generally based on MAC addresses. So can we use light as data and configure wavelengths as aliases to different MAC addresses? Optics has always been a promising field in communication. Let us extend their usage further. Can we make the core network infrastructure simple that allows for an easy maintenance and less time managing the queues and more time transferring the data? A probable way is to ask nodes themselves to handle the data they receive, thereby allowing the core to be free of buffers. Also, cloud traffic has been highly analyzed and the loads tend to flow in a similar pattern. And we take this as an advantage and completely get rid of the demand scheduling. A promising system developed by Microsoft is Sirius that employs the characteristics of one, optical switching, lasers, that is the long-range light generators, helps in transferring data in terms of light and helps in switching between endpoints. The core here is passive, which means it is free of any movable parts and consumes very less power compared to CMOS or electrical switches. Here, we route the data based on wavelength, unlike the previous way we used MAC addresses. To achieve faster reconfiguration, the team developed a custom tunable laser that has a latency of less than 5 nanoseconds. Let's talk about higher level design now. The system has collection of communication nodes connected using fiber called uplinks. Each node is a tunable laser and it is used to send and receive data. Tunable lasers is used to generate lights of varying wavelengths. The interconnection among these nodes can broadly be categorized into two sections, server-based deployment and rack-based deployment. In server-based deployments, server uplinks use tunable transceivers encode light wave based on the base, and the encoding is done using the information that is being transmitted, and the reverse is done for the decoding. This kind of design is huge because because of the number of interconnections. The rack-based deployment contains large number of rack switches. The servers connect to rack switches and their uplinks use tunable transceivers to encode and decode data. Use of rack switches has less complex design and as the system appears to be light and unlike the bulky server-based deployments. Let us get into the finer details of optical switching. How is it achieved and performed? The foremost thing is the generation of light. Hence, the system employs a laser as a source of light. Semiconductor lasers are the most preferred. They have a gain section that generates a range of wavelengths. Now that we have generated a range of wavelengths, we now have to find a way to actually send the light into different directions or into different endpoints. To achieve this, we employ the gratings. In specific, we use specialized array wavelength gratings, abbreviated as AWGR. Their sole purpose is to diffract light in different directions using slits. It contains a large number of slits arranged in the order, hence the name AWGR. By using laser generators and AWGRs, we can approximate the functionality of a switch.
In this context, the switching refers to the ability to generate a different range of the wavelength on dynamic basis. It is essential to understand that the cloud workloads have a robust behavior, which means that the switches could communicate with the different endpoints and the destination at the same time. This is known as high fanout, which is characterized by a large number of the output receiving data from the input. Supporting these heavy workloads requires the switch to have the ability to maintain high network utilizations and faster reconfiguration. So this is why the engineers hope that the latency of the reconfiguration must be less than 10 nanoseconds. The standard semiconductor lasers are unable to achieve this 10 nanosecond light switching, so the series employs a customized tunable laser to achieve a faster reconfiguration mechanism. But how is this achieved? In order to generate a range of the wavelength, we need to tune the tunable laser the same as any other waveform generator, so that each wavelength expels some tuning current. When you want to change from one wavelength to another, say lambda 1 to lambda 2, we need to change the current. However, this process is not perfect. When we try to change the current into a specific value, it will lead to some oscillations across the wavelength adjacent to a destination, and we call this effect as the ring effect. We need to minimize this ring effect, so in an attempt to dampen this effect, the series try to intentionally overshoot and undershoot the current, thereby achieving a very light error in the wavelength generations. After damping by overshooting and undershooting the closest tuning latency, the system is able to achieve closer to 14 nanoseconds, which is 4 nanoseconds greater than the desired. However, this still does not achieve the 10 nanosecond delays as we mentioned earlier. What could be the cause of the more latency? We're trying to couple the laser generator and the laser selector, so the selector works only after the light of a specific wavelength is generated. So can we parallelize the task to minimize the delay? So we separate the generator and selector, and this is called disaggregation, and this allows more flexibility in designing the components and also offers more robustness. So in order to parallelize, we need to ensure that there exists some of the work that can be parallelized. And when we're tuning the laser, what we are doing is tuning the laser one by one and then allowing it to pass through the gratings. When we have a disaggregation in action, then it allows us to use a multi-wavelength generator and to have the wavelength generated in parallel. The most simple method that comes to the mind when talking about the multi-wavelength sources is making the set of the fixed laser banks. But the disadvantage of this kind of a laser bank is that they lack the scalability because they can generate only a set of the pre-programmed wavelength. And if we want the new wavelength, we need to add a new laser generator. And this is also indicates that it will also increase the power consumption. So we can use a tunable laser bank that we have been mentioning all through the beginning. The tunable laser can generate a multiple wavelengths. So using a tunable laser bank, if we know in advance that we wish to tune the wavelength from lambda 1 to lambda 2, then the first tunable laser could emitting the lambda 1, while the second one is tuning to lambda 2 concurrently in order to get rid of the tuned latencies. And these banks are connected to the selector, which are used to select the wavelength. The series uses a combination of the tunable lasers and gratings to provide the abstraction of the single high radix switch. It can be used to connect the thousands of the server to form a high performance network cluster. And each node connected with the tunable laser banks and the gratings in this way allows each node to send the data to all the other nodes connected to the output of the grating by just changing the wavelength of the laser. So far, so good. We have talked about the important aspect of the switching and the connection between the endpoints. So now let's now talk about the routing and the scheduling. It is the most important part in the core network that allows the data flow. We were told that there are no buffers in the core network in the series and nodes managing their own queues. So it indicates that the series need a good traffic scheduling method to avoid in-network congestion. However, it is impossible and also not efficient to collect the demand and to figure out how to schedule at the nanosecond time scale. So the series make use of the static scheduling, which is also called scheduler-free system, instead of the time-consuming and demanding scheduling. In addition, the series designer discovered that the traffic flows similar pattern, so they used an approach called optimistic routing. And this technique of the routing ensures that no uplink receive data from the multiple nodes simultaneously, and which is the main functionality of the scheduling system. And also, we use the traffic patterns, and we do not require critical computations of dependent metrics that tell which route to use, and it takes up the precious amount of the time and the space. The series try to connect the two nodes at different times where a different number of the intermediate nodes, it tries to enforce load balancing. So it goes like this. The data from each node is routed across all the other nodes, which then forward the traffic to the destination. So since we're already having the static schedule, the data center demand metric is converted to a uniform demand matrix. For example, any given node has the same amount of the traffic to send it to all the other nodes in the data center. This in turn results in a key property where the series only need to provide equal rate connectivity between all the nodes, hence we have a load balancing features. So the information on this slide is worth a ton of reading, and let's go through it slowly and then put it with an example. In a data center with the n nodes and with their aggregate uplink bandwidth b per nodes, each node pair only needs to be connected with the b divided by n bandwidth, which is a perfect match for the series topology. Each transceiver of the node is tuned across the wavelength acrossly, and each node is connected to a different set of the gratings, and each node can also talk to the other nodes at the output of the grating in a round-robin fashion. So now let's consider there are 4 parts, and this means the network schedule repeat every epoch comprising 4 time slot. Suppose we are having all the nodes alternate between the wavelength from lambda 1 to lambda 4. So each node communicates to every other node once every 4 time slot. At any time slot, no nodes receive data from the 2 slots simultaneously. Now let's talk about, we already talked about how the routing, scheduling, load balancing is, and now we can talk about how the unit of the packets are forwarded in the server based on the rack-based deployment. In the server-based deployment, the packets are routed from the source to an intermediate server to the destination. But in the rack-based deployment, we can have the 2 kinds of the traffic over here. The first one is intra-traffic. It means that the traffic is between the nodes connected to the same rack switch, and this kind of the traffic is forwarded directly to a destination node from the rack switch. The second one is inter-traffic. Inter-traffic means the traffic is from the source node connected to the one rack switch to a node connected to another rack switch. So this kind of the traffic is queued and forwarded to the intermediate nodes. And see, this queuing is done at the intermediate nodes, and the core is free from any sort of the buffers. And from the intermediate nodes, they are routed based on their destination. Whenever we discuss the packet forwarding, we need to talk about the impact of the throughput and the latency. The service uses a data center wide schedule based on a static schedule mechanism. And this data center wide schedule in some way can affect the throughput and the latency. However, the experiment with the different flows and the loads on the series show that due to the load balancing, the worst case throughput happened to be 2 times larger than the traditional switching. So in order to reduce this, we can have the intermediate nodes and the primary points in the routing connected to a more number of the uplinks, and more uplinks means more node interconnects during the same epoch, which in turn increase the throughput. And adding the uplinks is easy since the core is passive. Just a number of the fabric connection can do the job, and it can be and also can have a very low cost and low power consumption. And the same is the case with the latency. Because of the data center wide schedule, each node has to traverse through almost every node due to load dependency, and this leads to a lot of detouring activity. And this lot of detouring can make an intermediate node receive the data from multiple sources, and this needs a lot of intermediate queuing if the data has to be sent to the same destination. So this filling up the queues due to data being signed to the same destination node can lead to congestion. To prevent network congestion, the service adopts a request and a grant system. The request and grant system means if the source node would like to send its package to the destination node, it should require the permission from the intermediate nodes before forwarding its packet. This method could prevent the intermediate node from getting overwhelmed with more packet than they could handle, and the service could also efficiently regulate the data transmission through the network and provide better control over the throughput and latency.
Having discussed a lot about most of the system, let us think based on the discussion so far whether the system is promising and is it worthy compared to the traditional ones. Seems like the answer is yes based on these reasons. The core topology is flat, meaning there is no hierarchy unlike traditional systems where CMOS forms a cascade and the groups are in turn cascaded, leading to a complex system. Series is devoid of such complexity, hence more robust. The core has no moving parts and power-hungry switches, hence less power cost and less cost in replacement. No buffers, hence no need for efficient buffering algorithms. Hence, network administrators can think of more important aspects. Scaling is simply easy, just by connecting more nodes. Electrical switches need timely replacement based on the speed demands and wearing. These optical switches are in stark contrast to these. These need not be upgraded. Further, due to load balancing, the wearing is minimized, hence less cost in maintenance. The most important thing that we haven't talked about is the timing synchronization. Let's dive into the details right away, as we all are aware of this and why is it important and how Sirius achieves it. Sirius requires node to be synchronized with an accuracy of less than 100 picoseconds. Let us talk about two important techniques in achieving time synchronization. They are phase locked loop and delay locked loop. Let us talk about PLL. It's an electronic circuit that can generate an output signal with a specific frequency and phase that is locked to a reference signal. The circuit works by comparing the phase of the reference signal to the phase of the output signal and adjusting the output signal's frequency and phase to match the reference signal. DLL is also similar kind. It is a type of electronic circuit that is used to synchronize digital signals with a known reference signal. It operates by detecting the phase difference between the reference signal and the digital signal, and then generating a control signal to adjust the delay of the digital signal to match the phase of the reference signal. What all components are necessitating timing synchronization? Is it due to tunable laser or gratings? Let's talk about gratings. Gratings are passive and they do not have any effect on timing because they do not have any timing associated with them. So this easily allows receivers to extract the clock of the sender and adjust its clock to match the frequency using phase locked loop or delay locked loop. To achieve this, the better approach could be to designate a server to be a leader node and let all other nodes adjust their clock based on the clock extracted from the leader every epoch. So this falls in line with the topics discussed in class about leader election and consensus. Also, to prevent failures and to allow higher robustness, Sirius automatically switches leaders during every few epochs in an RR fashion. Also, PLL or DLL helps in filtering out large changes in frequencies of the clock, thereby tackling Byzantine failures. By properly implementing this, the protocol ensures all the clocks tick at the same frequency. However, to achieve proper time synchronization, we also need to correctly estimate the propagation delay between any pair of nodes and their relative time offset. Since the core is passive, it is possible to accurately and efficiently measure a node's distance from AWGR, and it is critical to ensure a correct behavior of the system when fibers connecting the nodes to the AWGR have different lengths. So the key takeaway point is that each node starts its first epoch at a different time depending on the distance from AWGR. Hence, if the distance is longer, it starts sooner. So if the distances are factored out and packets belonging to the same slot will arrive at the AWGR at the same time, thereby aiding proper synchronization. Are the components, disaggregated lasers, gratings are any better on a holistic view? Let us talk about the CMOS dependency. In rack-based switches, we need some electrical switches to connect racks. In the post-Moore's law, with series, even if the free scaling of electrical switches slows down, the relative gains of series are far higher than traditional switcher networks. Let us also talk about the end-to-end reconfiguration latency. All the way we talked about reducing tuning latency, also latency due to synchronization. However, there is also an unaccounted latency with the end-to-end path reconfiguration during every epoch. Because these epochs repeat, the main idea is to cache such system parameters instead of learning them from scratch every time, which in turn minimizes the latency for clock recovery. We can also use amplitude caching to achieve amplitude stabilizations instead of slower gain control circuitry with complex feedback techniques. Laser sharing is the ability to allow transceivers to use a common laser. Series with disaggregated tunable lasers has a little trade-off in terms of complexity and chip area. However, due to load balancing and cyclic schedule, it allows all the transceivers on a node to use the same wavelength at any given time slot, thus mimicking laser sharing. But this complexity dominates the normal sharing due to its end result of achieving a sub-nanosecond tuning latency, which is very important. Now, let us talk about fault tolerance. Serious passive core provides future-proofness and robustness to failures due to the lack of any mechanical and electrical components. The transceiver is designed with fault tolerance in mind, separating lasers from the rest of the transceiver to make them field replaceable and help with shade backups. Also, load balancing routing can increase the blast radius of failures, but interconnection of rack pairs every few microseconds allows for low overhead yet fast failure detection, ensuring quick data center-wide communication of any detected failures to prevent black holing of traffic. Any node or transceiver failures only result in a proportional loss of network bandwidth, and the network schedule for all nodes can be adjusted to omit the failed node to regain any lost bandwidths, although at the expense of extra mechanisms for consistent updates of the node schedules. Now, having discussed about all the important design aspects and other aspects of the system, let us now evaluate the performance of the system. The main performance aspects are throughput, latency, and power consumption. Let us talk in detail about all the three aspects. Let us discuss about high throughput. Series achieves high throughput by leveraging the wide bandwidth of optical fibers, which can transmit data at very high speeds. The system uses wavelength division multiplexing to enable multiple optical channels to be carried over a single fiber, increasing the overall capacity of the network. Series also utilizes parallelism with multiple transceivers per server and a flat network topology that reduces the number of hops data packets must traverse. These design choices allow Series to achieve a throughput of up to 35.2 terabits per second in a single data center, which is huge. Now let us talk about latency. Series achieves low latency by using nanosecond scale optical switches, which can route data packets in just few nanoseconds. These switches are faster than electronic switches, which typically take microseconds to operate. Sirius also minimizes the number of hops that data packets must traverse, which further reduces latency. The system uses a single layer network topology, which eliminates the need for hierarchical switches and reduces the number of switches that each data packet must through. This in turn reduces the time it takes for data packet to travel from its source to destination, hence finally yielding low latency. Let's talk about the power consumption. Sirius achieves lower power consumption by using passive optical component such as gratings rather than active electronic components such as switches and transceivers. Passive components do not require any power to operate, reducing the overall power consumption of the network. Also, the system uses tunable lasers, which consume less power than fixed lasers, and optical bypassing, which allows data packets to be sent directly from one server to another without passing through a switch. This reduces the number of switches that must be powered on at any time, thus further reducing power consumption. The overall result is a network that can achieve high throughput and latency while significantly less power than traditional data center networks. Now let us talk about the cost and power analysis of Sirius. Sirius flat topology results in a significant power and cost gains over electrically switched networks. The single layer of gratings in Sirius can reduce network power and cost by almost 3/4 compared to the hierarchy of power-hungry switches and transceivers in ESN. Sirius power consumption is only 23 to 26% of electrically switched networks, even when tunable lasers consume 3 to 5 times more power than fixed lasers. Sirius cost is only 28% of ESNs, when the cost of gratings is only 25% of the electrical switches, assuming a tunable laser is 3 times the cost of fixed laser. So, keep talking about all these points, Sirius seems to be promising, and also it seems to be actually a very good promising candidate compared to the traditional switching networks, and it seems to be satisfying the future demands. So it's a very good system and a very good paper. Thank you.